So now we can combine those last two things together. Using the idea of limits, I will now be able to find the slope of tangent to any curve, not just semicircles, not just straight lines. So here is a random curve, y equals some function of x. I want to find the slope of that line there, tangent at the point P. That will be the slope of the curve. Now I say, well, I can estimate it with a secant, so I'm going to draw a secant in, but this time I'm going to make one of the endpoints of the secant the actual point of contact, so P. So PQ, and clearly looking at that, that's a bad estimate. But it is an estimate. So the question is, where should I put Q to get the best possible estimate? Now, as you should imagine, if you slide Q, if I slide it closer and closer to P, then that green line is going to get a better and better estimate. Ideally, I would like Q to be at the same point as P, because then it'll be perfect. Of course, it can't be. But what we can do is we can investigate the limits as that approaches zero, that distance approaches zero. So we want to put it as close to P as possible. Ideally, they're touching, so there is no distance in between them. That's what we'd like to do. I'll just expand that out a bit. So P, we know the coordinates. It's going to be x, it's going to have some function. Q, going to be some distance away, x plus h. Y value will be function x plus h. So the slope of this secant would become this expression here. Function x plus h minus function x all over h. But as I say, to find that exact value, what we've got to do is find that limit. What's it heading towards? Because the limit will give us the exact amount that we want. So there's our formula. The slope of the tangent will be the limit as h approaches 0, and h is going to be my distance in between the 2 points. Function x plus h minus function x over h. That's what's known as the derivative. But more than just the derivative, we say it's the derivative of y with respect to x. Because what we're saying is, how is y changing as x is changing? So tell me about y as x changes. Symbols we use. The y dx, probably the most common one. Where does it come from? Probably a derivation from using delta for change. And of course the Greek letter delta looks like a bit of a D. Well, the lowercase one, not the capital one. That's a triangle, isn't it? Y dash or apostrophe, y dash or y prime, I've even heard that one called. F dash x. And there's this other way of doing it, is simply saying, well, I just want to differentiate this function, so they write the actual equation of the function in there, with respect to x. Basically measures the rate of something changing, and that's a really useful thing to know about, because so many things change. And that's what we want to find. Now, instead of writing the word slope of tangent, I'll just give it its notation, f dash x. That formula there is known as differentiating from first principles. This expression of first principles happens a lot, because basically it's saying it's using the first idea. This is the first idea of calculus. So differentiating from first principles. So let's do it. Now look, I picked a straight line because we know what the answer should be. It's a straight line, we know the slope's 6. Here we go. Function x is 6x plus 1. So function x plus h, substituting x plus h in, 6x plus 6h plus 1. Let's put it into our formula. Now nicely what should happen is we get a whole heap of cancelling happening on the top, and I get left with something like this, which I can't do a direct substitution into because I'll get 0 and 0. That's the problem with the limit. I mean, you can't physically be at the same point. However, I should get something that cancels. And the h will cancel with the h, leaving me with 6. So what is the limit as h approaches 0? 6? Well, it's 6. There's nowhere to put the h. And so there's our answer. The derivative is 6. There's the slope of the tangent. Well, let's do a quadratic then. Y equals x squared minus 5x plus 2. In fact, we're going to find the equation of the tangent, not just the slope. Because we need a point, we need a slope. We've got a point, let's find a slope. So there's function x. Function x plus h. Sub that in, and I'll expand it out because I'm going to have to do that at some point anyway. Function x plus h minus function x over h. Here we go. And we should see everything there that doesn't have an h cancel, which means now I can divide the h into the top and I got an expression. I can sub 0 into that and get an answer, 2x minus 5. So there's our derivative. Point about the notation. See how that limit as h approaches 0 appears on every line until I substitute in. Because we say, hey, it's the limit of this, which is the same as the limit of this, which is the same as the limit of this, which is the same as the limit of this, which is this. So that stays on every line until you substitute in. Now we want to find here, because remember, this is not the slope of the tangent. This is the function that finds the gradient function. We need to substitute a value in to find out what the answer is. And we want when x equals 1. So when x equals 1, we know the slope of that curve is -3. Point slope formula, there it is, y equals -3x plus 1. Welcome to the wonderful world of calculus.